So welcome to demonstration video 2 as part of our course G04 on mutation detection. This video is on snip calling and intel calling with freebase. So that will be followed by the equivalent ones for BCF tools and the other steps mentioned previously. So remember that freebase is a computationally slow but effective mutation caller that performs de novo assembly to resolve the local haplotypes more effectively. So therefore it is good at determining the resolution of highly variable regions with many mutations at a single locus. It can be slow, and therefore you should use it with caution for large vector or host genomes because they will take some time. So if we remember this diagram we had before, we're looking at our reference genome here. We might have reads that contain different alleles compared to our reference. And if they're quite dense, de novo assembly can work effectively to identify the true variants that are present and not ones that maybe are not really real. And therefore, we may be able to identify the haplotypes that are most likely based on the patterns in the reads themselves, based on the linkage between different alleles. And therefore, we can ignore ones that are more rare or less likely and perhaps are associated with being errors. The same applies for homopolymers or other structurally more difficult regions to resolve. We can estimate their actual repeat size more effectively. Our command structure for this is outlined here. So we call the tool itself. We determine the reference facet that's of interest. We look at -F here indicates the minimum allele frequency here, which is 0.01. You can change that to 0.02 if you want. We have -G2000, the ignore bases with coverage that's higher than that because that might contain a structural variant. -P1, we're assuming that they're haploid because we're dealing with virus, SARS-CoV-2 virus genome data here. We're expecting a minimal alternate allele count of at least 6 in our case. So you could replace that with 6 or a higher number if you want to be more stringent. Minimum alternate allele fraction of 0.02 for M here. And that's because we can be as low as that if we have very high coverage. If we don't have high coverage, this won't work as well. We'll get more errors. And then this is our input file, and we're sending this all to the BCF file as output. In the same way, we're going to use BCF tools as well. That's a multifunctional package for BCF and BCF file processing. And it kind of uses a process of estimating the probability of having the reference allele given the data and the prior allele frequency spectrum. And if this is lower, like this probability is below 0.9, that might indicate that's a mutation. It's not absolute, but it might be indicative that it's a mutation. So what we can do is bear in mind that it runs particular statistical tests to screen out mutations that might be erroneous because they contain many forward or reverse reads and not the other type, because that could be associated with PCR artifacts. Command structures like this, we have BCF tools, and our function here is mpileup. We restricted that to be a maximum of 2500 here. And then we're making pileup output to be sent to BCF here, OB. And then we're using this reference, and our input is the command file. Then this is the first part of the command. So the next step is to pipe it out to BCF tools call, which you can see here. And we're using a CVO, which corresponds to use the call function using uncompressed BCF output with the POID set to 1 because we're dealing with virus data. And we're sending this output to output.bcftools.bcf.gz. So you'll see that it's the compressed format that we're using here, .gz, for BCF files. So this video kind of outlines how we can call snips using freebase and BCF tools. And now we'll switch to the server to actually apply these commands directly. So now we're going to call mutations using freebase, and we're just going to paste in the command we had before. What we might do then is just these items depending on what our input is. So in this example, what I might do is use a particular sample, let's say ERR 977 we see there as our input. So we're going to change that to ERR, maybe I can put a space in here, ERR 9 7719. That's our BAM, but we're going to add on, it's the full BAM extension is sorted.ormdupe.bam. Our output file is going to be then error9.freebase.vcf. I'll do. Our minimum alternative allele fraction is 0.02. Minimum alternative allele count, let's use 6, and the other parameters are okay, except the reference that needs to be our SARS-CoV-2 reference NC there, and we should now, have that working to call our SNPs. It will take a moment because this takes some time to run. Let's look at our output to see if it worked. And this is the header of the VCF, which we'll talk about in the previous video on the introduction material. And then we see now that we've called SNPs going through, and you see there's a lot called there, and we can estimate them just by grepping to count, excluding sites that contain a hash. So let me just find the hash key. So we see there now that we have 65 potential candidate SNPs. If we're then going on to do the equivalent command with samtools mpileup, we can just modify our input in the same way. ER9 was the one you have there. We're putting that in as BAM input, but we're looking at the sorted.ormdupe.bam file. We're going to change the output to reflect that name again. ER9. There we go. And everything else is the same. We can change this to maybe be 2000 to be consistent. And that should run. If I spell the BAM file with the right name and M at the end. So you see that's processing now. It says it's one sample in, one input file. It will always give the output, and we'll say the parameters that we're looking at. So what we're going to do is gzip.decompress this file name to see what's inside there. So you can see we have lots of SNPs there being called, and we can recycle our command we had before for this file, except we're going to put gzip-dc at the start, and then our file name is vcf.vcftools.dz, piping it out to grep, and that counts the number of SNPs that we're seeking to find. So you can see there, well, we have 58 that are determined there. So these might need further examination. You can see even the last 3 here that are all adjacent to each other. That would be surprising if that's real. You see that the depth there is quite lower, much lower compared to the adjacent regions, and also that it's coming towards the end of the genome, where the resolution of the exact base composition is often more tricky. So that kind of concludes our brief video to introducing you to calling variants with VCF tools and Freebase. Remember that with Freebase, you can also compress your output just using gzip, like that. And then you can have that then as a gzip file. So that means you can apply the BCF tools output and the Freebase output. You can look at it using the same commands. And it's best to keep it as compressed output.